Hello and welcome. Now we are going to look at a question involving electromagnetism. Let us look at the question first. The diagrams shows a horizontal wire in a magnetic field. The horizontal wire is firmly held at each end and cannot move. The magnets and holder are on balance. When there is no current in the wire, the reading on the balance is 0.35 gram. So based on the question, the balance here is actually being used to measure the weight of the magnet. But of course, internally, the balance has done some kind of a calculations correction using the formula W equals to mg, so that the balance is converting the weight into mass. So it is given that the balance measures the magnet to be 0.35 gram, or in other words, the gravitational force acting onto the magnets is approximately 3.5 newtons. Now there is a DC current, which is a direct current here, in the wire as shown, which is shown in this diagram. What happens to the reading on the balance? Now to do these questions, we need to understand two theories here. The first theory here is on the Fleming left-hand rule. Now we recall that anytime you have a current, there will be a circular magnetic field around the current. And that magnetic field will interact with any external magnetic field. In this case, the external magnetic field is provided by this U-shaped magnet over here. So due to the interactions between the magnetic fields caused by the wire and the magnetic field caused by the external magnets, a force is induced. To figure out the direction of that force, we need to make use of the Fleming's left-hand rule, which I have copied this diagram from Wikipedia. So just for a quick review on Fleming's left-hand rule, the middle finger of our left hand is used to represent the direction of the current. The index finger is being used to represent the field. Now in this case, it's specifically a magnetic field. And the thumb is to represent the direction of thrust, or basically the direction of the induced force due to the interaction between the current and the external magnetic fields. So we first identify the direction of the current. Now very obvious, in this case, the current is going down the page. On the other hand, our magnetic field will always go from the north pole to the south pole. In this case, we can see that the direction of our magnetic field is going to the right. Therefore, if we make use of the Fleming's left-hand rule, our middle finger, which is used to represent the current, must be pointing down the page. And our magnetic field, which is represented by our index finger, must be pointing to the right. And if you position your left hand correctly, you will see that your direction of your thumb will naturally coming out of the page. But of course, this diagram here is just for the view from above. If we look at the view from the side, then the direction will change a little bit. In this case, you can see that our current is coming out of the page, and our magnetic field, which goes from north to south pole, in this case is still pointing to the right. So again, we make use of Fleming's left-hand rule, where your middle finger, which represents the current, is now pointing out of the page, and your index finger should be pointing to the right. So you will naturally see that your thumb is pointing upwards. However, with just this theory, it is not sufficient. At this point, by using Fleming's left-hand rule, we have only figured out that the direction of the force onto the wire is going up. But in this question, we are trying to find out what is going to happen to the reading on the balance, which is used to measure the weight and hence the mass of the magnet. Therefore, in this case, instead of the force acting onto the wire, what we really want to find out is what is the amount of force that is actually acting onto the magnet. Now at this point, a lot of students will say that because the Fleming's left-hand rule allow us to find that there's an induced force upwards acting onto the currents, and therefore there's no force acting onto the magnets, and therefore the reading will not have any changes. That is unfortunately incorrect. This is because we need to take into account of another theory, which is the Newton's third law of motion. Now, just for a very quick revision, we know that Newton's third law of motion tells us that for every action, there is an equal but opposite reaction. For example, if we have a person standing on the ground, so the person actually exerts a certain amount of gravitational force onto the ground. However, due to Newton's third law of motion, the ground must be exerting the same amount of force but in opposite direction as the weight. And that force is what we call the reaction force. Now let's consider another example. Let's say we have two persons, A and B, and they are both standing on a slippery ice surface. Let's say the person B is just standing there, but the person A is actually pushing the person B. Now, even though the person B is just standing quietly all the time, as long as the person A is exerting a force by pushing onto person B, inevitably, the person B will exert back a reaction force back to A. Essentially, if person A is exerting a rightward force onto B, then B is also exerting an equal amount, but in the opposite direction, which in this case a leftward force back onto A. And this is the basic idea of Newton's third law of motion. If we try to apply Newton's third law of motion back onto this question, we know that due to the interaction between the magnetic field by the magnets and the magnetic field by the current, there is an induced upward force onto the current. So if we take the perspective of the magnets, we may think that the magnetic field of the magnet is exerting a force upwards onto the wire. Hence, due to Newton's third law of motion, for every action there's an equal but opposite reaction. The magnet must be experiencing an equal but opposite reaction from the induced force, which means that we expect this magnet will experience an equal amount of force downwards. Therefore, by comparison, when there is no current in the wire, we know that the force that is acting onto the balance is only the weight of the magnets. So hence, we know that the weight of magnet is approximately 3.5 newtons. But now if we have a current in the wire, now there are two forces. You still have the weight of the magnets, but at the same time, due to the reaction, there is a downward force acting onto the magnets. So the total force onto the balance is the sum of the weight of magnets and also the magnetic force, which means that we expect the reading to be higher than 0.35 gram. Therefore, the answer should be D. And that is it.